Hi viewers, this is Rohit Singh along with Ravinder Singh Sivaji Das from Weltech University. We prepared this video to demonstrate our final year project on a study of performance and emission characteristics of biodiesel in single cylinder VCR engine. This project is guided by Rohit Renis, Assistant Professor Mechanical Department, Weltech University. Our main objective is to extract the oil from the Argemone seed to obtain biodiesel using suitable transesterification process, to study the engine performance and emission characteristic of VCR engine using Argemone oil as a biodiesel. These are the methodology: oil extraction, transesterification process, engine performance and emission characteristic, finally result analysis. Process involved during the project: collection of Argemone seed, conversion of Argemone seed into Argemone oil. Argemone oil is allowed to react with methanol and a catalyst. This is the transesterification process. The product we obtain from this is allowed to cool down for 20 hours to separate the glycerin from the byproduct. Then this byproduct go for water wash to get the clean biodiesel. Biodiesel mainly are the fatty acid or biodiesel can be made from new or used vegetable oil and animal fats which are non-toxic, biodegradable and renewable resources. Fats and oils are chemically reacted with an alcohol to produce chemical compound known as fatty acid methyl esters. Biodiesel is the name given to the esters when they are intended for the use as a fuel. Region to choose Argemone seed. Argemone seeds are easy to find in the Asian environment. As Argemone plant does not need much fertile land, it can grow in hilly areas also. The oil obtained from seeds are in 5 ratio, that is 5 kg of oil, 5 kg of seed, it gives 1 kg of oil. The main problem of all seeds oils are viscosity. Here we have to apply less effort to get viscosity same as the diesel. This is the comparison between the oils. Properties: density in gram per cc, calorific value megajoule kilowatt per hour, cetane number, viscosity at 40 degree centigrade, flash point degree centigrade, carbon residue, fire point in degree centigrade. Diesel have density 0.840, Jatropha 0.918, Mahua 0.918 and Argemone 0.865. This is less from the Jatropha and the Mahua, but it is not equal to the diesel, but it is similar to the diesel. Only 0.02 difference is there. For calorific value, diesel 42.93, Jatropha 39.774, Mahua 38.863, for Argemone 41.5. Again we see that the difference between the diesel and Argemone oil is little bit different as compared to Jatropha and Mahua. As we know, Jatropha and Mahua are the finest biodiesel till now we have found. Cetane number 45.5, 45, 34 and the 51. Viscosity for the diesel is 4.59, for Jatropha 49.9, Mahua 68.51, Argemone 4.4. Flash point for the diesel 75, Jatropha 240, Mahua 238, Argemone 170. Fire point for diesel is 78, for Jatropha is 244, for Mahua is 244, Argemone 184. Here we can see clearly that in comparison to Jatropha and Mahua, the Argemone oil is better, as the properties of the oil is little bit different from the diesel, but as is similar to the diesel. We gone through many papers and literatures, then we are able to conclude that No studies on thermal performance and emission characteristics at different present compression ratios using these biodiesel has been performed along, although many studies have been conducted at a constant compression ratio. So we decided to take the all readings at a different compression ratio, and we absolutely go for the blending. Blending actually is the mixing of biodiesel and diesel to get the better performance. Oil extraction. It is the first process involved during the experiment to extract the oil from the seed. The Argemone oil obtained is by the solvent extraction process. In this process, the ethanol is converted to vapor by heating at 70 degrees centigrade and then condensed, and then it is made to react with the seeds to extract oil from it. From the figure it's easy to explain. Here we have ethanol. It is get heated with the help of this tube. It allowed to condense here and it allowed to react with the seeds. Then the oil we obtain from this small tube. This is the Argemone seed, left hand side, and the right hand side oil of Argemone seed, what we get. The second process involved during the project is transesterification process. Transesterification is the process of exchanging the organic group of an ester with an organic group of an alcohol. Actually, this is a chemical reaction transfer of carbon chain. The reaction are often catalyzed by the addition of an acid or base catalyst like KH. Transesterification process. In this stage, the Argemone oil is made to react with the methanol and catalyst. The catalyst is added to methanol so that it can react with the oil. KOH is used as a catalyst. The ratio between methanol and oil is 6:1. The mixture is stirred for 40 minutes. This is the setup of transesterification process. Biodiesel and glycerin separation. After the transesterification process, the mixture is transferred to the separating flask. It is left to settling for 24 hours. There will be two layers formed, out of which one is biodiesel and another is glycerin. The glycerin is removed from the separating flask. Next, washing. Once we separate biodiesel from glycerin, the last stage to obtain pure biodiesel is washing. Washing is basically done to reduce the pH value. Washing is done 3 times so that the pH value is reduced to 5. Hence, pure biodiesel is obtained. This is the experimental setup of our project. This is the tank area. Here you can put petrol or diesel. This is multi-fuel engine. Then we have set up for all the outputs. In the computer will give the all outputs. All the sensors are connected to the computers. The biodiesel allowed to pass through the magic mirror so that we can know the exact amount of oil what is going inside the engine. This magic mirror is connected to the VCR engine, that is variable compression ratio engine. The air box is connected to give the air supply to the engine. In engine we know all the process happening. After the combustion of fuel, the exhaust gas is allowed to go through flue gas analyzer, and we have dynamometer to apply load on the engine to get the result at a different loads. These are the properties we obtain from the setup. Test description: density in kg per meter cube, viscosity in CST, calorific value megajoule per kg, S content percentage weight, flash point degree centigrade, fire point degree centigrade. For the pure biodiesel, it is density is 865, and for diesel it's 831. But if you go for different blending B10 and B20, we can have also the different density that is less than the B100. It is quite more similar to the diesel 831 and 842. If you go for blending B10, 10% of argemonal and 90% of diesel. Viscosity for the diesel is 3.2, for argemone is 4.4, but if you go for blending for B10 it's 2.9, less than the diesel. It gives the more burning of fuel. In the cold winter season we are not able to have the problem of flowing of fuel. Calorific value for the diesel is 44.5, for pure argemonal is 41.5, but for the B10 it's 43.7. Only one difference in the as compared to the property of diesel. Flash point 76 degrees centigrade. For the pure argemonal 170 degrees centigrade, but for the blending B10 we have 68 degrees centigrade. Fire point 78 degrees centigrade for diesel. For biodiesel, for argemonal it's 184, but for B10 it's 72. Here we can conclude that if you go for blending for B10, we have the almost similar properties as the same as the diesel. Then we are not going to face any challenges, whatever the challenges we are facing in the other oils. Engine specification: 4-stroke multi-fuel engine, water cooled, 1500 rpm, 3.5 kilowatt power, compression ratio 12 to 18, swept volume 661.45 cc. These are the results we obtain on the engine. Emission of carbon monoxide for compression ratio 14. For zero load, B10 gives 0.042% of CO, B20 gives 0.031% of 0.031%, B100 gives 0.011, while diesel gives 0.045. That is highest among all these for B10, B20, B100. Likewise, for 10 kg of load, we have B10 CO emission for B10 is 0.07, for B20 0.041, B100 0.05, but for the diesel 0.082. Again we have the highest emission of CO in diesel. Likewise, we can easily see in 15, for load 15, the same data. We highest in diesel and the less in B10. 18 compression, 18 kg of load, same data, highest in the diesel. In the graph, it is easy to explain that here we have B10 slightly downside the diesel. This is blue line, so our diesel graph, diesel dependency. For B100 we have orange color. But for the B20 we have yellow green color. In this graph it is shown that if go for B10 blending, the CO emission is less as compared to diesel. If you go for B100, then we have lesser value of emission, but I will conclude in last that why we are not going for B100. For compression ratio 16, carbon monoxide emission. For 0.8 kg of load, B10 gives 0.05%, B20 gives 0.038%, B100 gives 0.026%, but for diesel is 0.061, highest among all. Like for 10 kg of load, B10 gives 0.062%, B20 gives 0.045, B100 gives 0.035, but diesel gives 0.072. It's same as little bit similar to the B10, but for as compared to B100, it's just about to double. For load of 15, B10 gives 0.092, B20 gives 0.082, B15 gives 0.058, diesel gives 0.101. Here in the graph, blue line shows the diesel, the highest emission. Then we have emission of B10, then B20, and the downmost side have pure Argemone, that is B100. Again, the pure biodiesel gives less emission of carbon monoxide. In CR14 and CR16, we see that carbon monoxide emission in Argemone is least as compared to B10, B20 or pure diesel. For comparison ratio 14, carbon dioxide emission. 0 kg of load, B10 gives 2.6%, B20 gives 2.5, B100 gives 2.1, but the diesel gives 2.9, highest among all. Again, 10 kg of load 4.8, for B20 4.9, for B100 4, for diesel 5.3. For load 15, B10 gives 6.2, B20 gives 6, B100 gives 4.8, diesel gives 6.4. Here in graph we have easy to explain that here the blue line shows diesel, highest emission. For the carbon dioxide also, we have already see that carbon monoxide high emission. Here we are seeing that carbon dioxide is also higher in diesel. Again we have B10 downside this line, then B20 carbon dioxide emission. For B100, this is downward side, means very less emission in pure Argemone, carbon dioxide. For carbon dioxide emission in CR compression ratio 16, for 0 kg of load, B10 gives 2.8% of CO2, B20 gives 2.4%, B100 gives 2.4, and diesel gives 3.3. This is the data of CO2 emission for compression ratio 16. In graph, this blue line is diesel. Again, for CR16, carbon dioxide emission is higher as compared to B20, B100, and the downmost side is B100. Very less emission in pure Argemone. NOx percentage. For CR14, 0 kg of load gives for B10 135, B20 152, B100 209, and diesel 121. Load 10 kg 187, B20 203, B100 260, diesel 175. In graph, it is shown that for diesel it is very less. In case of NOx for CR14, the emission is very less, but for B10 it's similar. For B20 it's more emission, and for pure Argemone it's highest emission. the result we obtain for CO and CO2 is just opposite. Argemone gives the highest emission of NOx for CO14. For compression ratio 16 NOx emission, 0 kg of load, B10 gives 139, B20 gives 162, B100 gives 241, diesel gives 151. In graph I am going to explain diesel. This is the diesel graph, blue line, and for the B10 just similar, side by side to the diesel. For B20 it's also little bit more emission but similar to the diesel. For pure Argemone, that is B100, we have highest emission. In the case of NOx, pure Argemone gives highest emission, but B10 gives same result as the diesel. Little bit difference is there. And here the performance test. Brake thermal efficiency. For 0 kg of load, B10 gives 0.17%, B20 gives 0.18, B100 gives 0.15, while diesel gives 0.4. For brake thermal efficiency, diesel is the highest. In fact, not only the highest but almost the 2 or 3 times highest in comparison to B20, B100. For the loads 10 kg, B10 gives 26.50, B20 gives 27.67, B100 gives 20.20, diesel gives 29.60. Here the results are not much vary as vary in the 0 kg load. For the load of 15 kg, B10 gives 30 ppm, B20 gives 29.50, B100 gives 25.60, diesel gives 32.78. It is clearly seen from the graph that the diesel gives highest performance. This blue line. Side by side we have green line, that is B10. Then B20. In the performance, in brake thermal efficiency performance, we have the highest power in diesel, but in B10 and B20 are less but not much vary, little bit difference is there. For the pure Argemone, the difference is quite large. For compression ratio 16, brake thermal efficiency for 0 kg of load, B10 gives 0.58, B20 gives 0.40, B100 gives 0.16, while diesel gives 0.75. For 10 kg of loads, B10 gives 29.50, B20 gives 27.80, B100 gives 25.12, diesel gives 29.26. In the graph, here the highest power, highest efficiency we are having in diesel. Then outside this B10 graph is there. Down to this B20 is there. And the last pure Argemone B100 is there. Thus, after completion of all test, emission test and performance test and the reading of all the properties, it is concluded that the biodiesel blend of B10 gives the lowest emission when compared to other blends, even though the performance is slightly lower than the diesel, but we can go for the B10 because the emission level of carbon monoxide or carbon dioxide is very less as compared to diesel. But as we see in the now problem is that greenhouse effect and the global warming, but if we go for B10 we can solve these two big problems for our coming generations. Thank you.